Thanks for joining this session. So we're going to be talking about a core engineering, railway engineering topic, as I call it, about tamping and ballast tamping. One of the reasons that RTSA and myself pick up this topic, it's very important. Ballast tamping is very important to railway, and I have quite a fortunate time back lecturing on a few universities around the world, and they always ask me why tamping is important. Well, I say that tamping is very important, just as your health. If you don't keep it constantly, you're going to notice after a while. Huh? So that's why it is good to bring up ballast tamping as a topic to provide this through RTSA and Engineering New Zealand. So before I'm handing it over to Adam, I'm just going to say quickly talk about the RTSA, Railway Technical Society of Australasia. What we want to do is we want to stimulate and contribute, participate the member to the development of railway technology. And of course, what we do here in New Zealand is always support the business of railway industry. We do a lot of webinar. We also out on the university to help out the university to get the railway into the engineering courses. If you are keen to know more about RTSA, I would recommend you to follow the link on the bottom of the screen here to get involved with me and my other committee members in the RTSA. But today's back today to the topic, a little bit about Adam. Adam started to working with railway after 10 years in the Royal Navy. Adam worked as a trackman on London Underground, carrying a lot of track renewal. So Adam is now doing been with Fugro 1.5 years, business development manager, rail maintenance, over 15 years of rail experience. So with that word and with further ado, I'll hand it over to Adam.
Brilliant. Thank you very much, Michael. I will just share my screen. So hopefully now everybody, there we go. So hopefully everybody can see that now. So yeah, good morning. Thank you, Michael, for the introduction, and thank you for the New Zealand chapter of the Railway Technical Society of Australasia for welcoming me today. So as Michael said, I've worked in the rail industry for some time, and I am very proud that a good amount of that was in the track environment. And I've always been very protective of the people that I've worked with or sent out to work on track, because as we all know, it can be a very dangerous environment to work in. And so one of the reasons I'm so passionate about Smart Tamp is one of the many benefits that it offers is the reduction in time that surveyors need to spend in a position of risk. You know, we're all part of this global high-vis orange army, and every single one of us deserves to be able to go home at the end of a shift. So into the presentation, and today I'm going to be talking about tamping, and then we're going to move on to the Fugro Ryler system, and then we're going to delve into InnoTamp and Smart Tamp, which is the product that came from that. So let's go straight into tamping. So as we know, routine maintenance tamping is an essential task to maintain a safe track geometry. During maintenance tamping, a tamper machine will collect data on the current relative track geometry and assess how much the track needs to be moved to bring it back into specification. Put simply, this technique removes short and medium wavelength defects to leave the track in a safe, compliant condition with minimal likelihood of derailments. However, over time and with multiple tamps, use of this technique can compromise the overall track alignment and introduce some undesirable longer wavelength features, produce compound curves and shift transitions, leading to poor cant build-up. But with design tamping, We assess the current track position independently of the actual tamping operation and then design the optimum track alignment, which takes care of short, medium, and long wavelength problems. A survey team is sent to site to collect the current track position, and then we design the track to an optimal position. The optimal position will then be input into a tamper machine's computer, and the tamper will be sent out to reposition the track to a design position. So this is also used in applications such as managed track position, absolute track position to maintain the through alignment design. So why do we currently carry out more conventional tamping than design tamping? Well, design tamping using traditional methods can be applied today. However, the traditional design tamping approach does have disadvantages. It requires staff on or near the track, which creates a safety risk, and the survey speed is slow. A design tamping shift will always require a separate survey shift within a possession, which reduces the network availability. And there's limited survey resources available. So for the UK, where I'm based, a total of 8,800 survey shifts would be needed to execute surveys across the whole of our 32,000 kilometres of track on the network. So this would equate to 352,000 on-track exposure hours per year. And our client in the Wales and Western region of the UK had this to say: when I was Safety and Assurance Director of Infrastructure Projects Track, we had a near miss on average every third week. When we analysed the problem, many involved plain line surveyors working during the day on open railways undertaking track geometry surveys. So at Fugro, we have a system that can really help with this and keep surveyors away from trains. From the track. We use our Ryler system to survey, and it's a system that can be mounted to almost any train, be it an in-service passenger train, a loco, or a maintenance train. The system is self-contained and can be connected to a passenger train in less than 2 minutes. The system is autonomous and requires no intervention from the survey or train crew during data collection. Ryler is a series of tightly integrated subsystems with positioning provided by GNSS and an IMU to tell us exactly where we are on the Earth's surface, producing coordinate-based information. The system has twin railhead laser scanners, which image the railhead, allowing us to determine the track position in X, Y, and Z, from which the geometry can then be calculated. And further, a 360-degree LiDAR scanner records the position of all of the assets around the track, such as overhead line equipment, platforms, tunnels, and gives us the ability to determine structure gauge. And finally, the system contains a high-resolution camera to produce geo-reference video, which can be used on a variety of applications. And actually also, Ryler's is powered completely independently, and the batteries last approximately 8 hours. So as I said, we can fit onto almost any train, and I'll start this video. So this is our operators connecting Ryler to a train in the Netherlands. And so the way we do this is we have an adapter plate on the right-hand side of the platform there, and we'll just check the coupler to make sure that that's in a safe and compliant condition. And then we will attach the adapter plate to the coupler. We have color coding on there to tell us when it's in exactly the right place. And you've just seen the lock pop up there to tell us in position. We do a double check and then we lock it down into position. And that is the attachment then to the train's coupler. After that, we will pick up the Ryler system, and you can see the 4 points we have there that will connect. And we just slide it over the top of the plate and into position. It's then locked, and we double check that the locks are in position. And then we put the GNSS antenna up, and we'll lock that down with the guide ropes. Pop the key out. A quick final check, and you will notice the timer in the top. We managed to fit that there in less than 1 minute and 30 seconds. So for the system is routinely deployed in the UK and across Europe. In the case of the UK, we're approved to provide absolute positional data of rail assets as documented in the Network Rail L2 3100 standards, and we also have a full product acceptance certificate within the UK. We've been working in the UK since 2013, and we've surveyed over 65% of the UK network so far. It's also been extensively tested through Europe. The track geometry vehicle, or simply put the measuring train, in this case ProRail's TRV in the Netherlands. And because this was a calibration survey, we did several passes under identical as well as varying measuring conditions, such as change in travel direction, change in Ryler's placement on the train. And this is allowed to check for repeatability and reproducibility of Ryler runs, and then also allows us to compare to other systems like the TRV of ProRail. So the repeatability is how two passes of the same system compare under identical measuring conditions, and reproducibility is how two passes of the same system compare under varying measurement conditions, such as Ryler on the front of the train for the first pass and the back for the second. And it's also a means of comparing data of one measurement system with another. So you can see on this chart here, the repeatability, you'll see two passes of Ryler under the same scope measured within a short interval of time under identical conditions. And this really does show how stable the system is. And this is a comparison with the ProRail TRV. And again, you can see that Ryler matches up very well for that. Actually, the black lines there, the outliers, were actually produced by the TRV and not by Ryler. And we can also look at the twist information on there. So let's move on now to the Tamp project. So this project was awarded by Innovate UK in June 2020 under the SBRI First of a Kind in Rail competition, with full grant funding provided by the Department for Transport. In total, this research call delivered about £9.4 million of funding into innovations for the UK rail sector, with Tamp being one of the 24 funded projects. The competition had several themes, with Tamp being applied to the theme of optimised and cost-effective maintenance, which in the cost of Tamp relates to the maintenance of the infrastructure. The aim of the Innovate UK competition was to demonstrate how proven technologies can be integrated into a railway environment for the first time. It aimed to encourage innovation in the rail industry through the use of novel technologies and innovative use of data. In the case of Tamp, this was to apply a technology already proven in other parts of the rail sector to maintenance activities and to investigate new uses of the data. And if a note for this slide, I've highlighted the word demonstrate, and this was actually a contractual obligation. The Tamp process was intended to be a practical application, excuse me, which can be implemented rather than blue sky thinking or just base principle research. So the project submission was supported by Network Rail, and I would still like to thank everyone at Network Rail who were involved, especially the technical authority in Western and Wales route, who provided both excellent technical support throughout the project and access to their infrastructure to enable us to demonstrate this approach. And I'm pretty sure that all of you can appreciate accessing an operational railway, coordinating activities with tamper operators, and trialling these approaches on track with a line speed of 125 miles an hour is not really a simple undertaking, and it really wouldn't have been possible if we hadn't had the full engagement from Network Rail during the project. But why did we think this solution would work? Well, we listened to our customers and we read a lot of research. So previous studies have identified that the savings of up to 30% can be made on rail maintainers' maintenance budgets by moving to a coordinate-based maintenance. So notably, as we can see on this chart, a study by the Swiss maintainer SBB found that over a 10-year period, they reduced their maintenance spend by 30%, whilst at the same time improving their track quality by 50%. And this was all during a period where traffic load was increasing. So this is a dream scenario for any maintainer. A similar study by JSC Russian Railways in 2017 found very similar savings on an overall maintenance spend and attributed a 10 to 20% saving to design tamping. So this makes design tamping the biggest single area of potential maintenance cost savings. This chart displays the types of defects seen at differing speeds and wavelengths. And the literature suggests that design tamping is an effective treatment to eliminate longer wavelength faults above around 30 meters on line speeds as low as 100 kilometers per hour, meaning it's a highly suitable technique for vastly more of a rail network than it's currently being used to maintain. You'll also note on this same chart that the recording cards which record relative track geometry struggle to identify longer wavelength defects. These tend to be the defects which cause vehicle body bounce, which increase the dynamic loading on both the track and the rolling stock, causing them to wear out quickly. If we can reduce the dynamic loading, this will help to increase the life cycle of both the infrastructure of rolling stock, the infrastructure and of rolling stock. We saw how much so this also causes a rough ride for both passengers and freight, and tools such as RILA, which are based on absolute coordinates, are able to detect features over longer wavelengths than relative track geometry systems, offering the ability to improve ride quality at higher speeds significantly. We've carried out research. We carried out our research project, and we can look at the objectives now. So the objectives of the project were to demonstrate how costs associated with design tamping can be reduced while also reducing exposure hours on track for workers by removing the need for traditional surveying to input into the design process. We've done this by demonstrating how data from RILA can be integrated into a design tamping process to provide positional data for the design and drive efficiency in the process by building a conceptual tool set to bring all of the relevant data into one single location. So we could look at the results of Tamp. Now, I always I've put the box at the end to show exactly where we carried out the design tamping. And you can see the blue line is design and the red line is the deviation of slews on RILA. So you can see that we were pretty close after the settling in period for it. So it's a very, very good design tamp. The bit before we wanted to do, but unfortunately life in the railway took over. And in fact, another tamping machine that wasn't allocated to us had broken down and meant we couldn't get a line blockage for 3 hours. And so we were only able to complete the last section of the tamping that we wanted to do. So what did we get from Tamp? Well, we now have a product called Smart Tamp. And Smart Tamp is a modified approach to design tamping. Smart Tamp focuses on applying the collected geodetic data to create an optimized safe track alignment. Geodetic reference data is post-processed to supply a 3D laser point cloud and data relating to absolute track position. This is then used to model the optimum alignment whilst maintaining gauge clearance to structures and appropriate height and stagger for OLE. In conventional maintenance tamping, the lift and slew of the track is restricted to 40 millimeters and 25 millimeters respectively from the original design position to avoid any potential clash between rolling stock and corridor infrastructure. By modeling the track in 3D space in relation to surrounding assets, it is possible to design the new track alignment with confidence beyond the previous 25 millimeter limit to achieve the optimum alignment for the smoothest ride. Once finalized, the designed alignment is converted into a corresponding track adjustments, lifts and slews, and can be input into the tamping equipment. The surface profile can also be used to accurately determine the current ballast volume and the tonnage of ballast needed to bring the ballast profile into line, providing exact locations of where to drop the ballast to achieve the designed track lift. So Smart Tamp is a comprehensive solution that offers more sustainable whole life geometry and increases track quality, which ultimately reduces maintenance costs and improves safety. So after seeing what we've done, let's have a little look at the following benefits that Smart Tamp can deliver. So a 30% cost reduction, 20% less wear and tear to trains and infrastructure, 97% less boots on ballast, increased tamper utilisation, and 20% lifetime extension of assets with a reduction of the consumption of fuel by at least 5%. With Network Rail, this is something I've worked on a lot, so we can find out how much they spend across their renewals and maintenance or other areas quite easy. So 1.65 billion is spent on track renewal and maintenance, and the percentage of the cost reduction based on what we've just seen, the coordinate-based maintenance, is set at 30%. So the long-term saving on track maintenance would therefore be 495 million per year. Design tamping contributes to 66% of these savings, adding up to a potential saving of 330 million per year. I will add some caution to these figures though, because they're for the whole network. So to achieve this figure, it would take a gradual rollout across the main routes and then would tackle other areas. And to be open, I haven't also added the costs of designs, but these track designs should not cost 495 million. And again, so we spoke earlier on about with Ryler, the Ryler crew is on the track only at the beginning and end of the shift, whilst mounting the survey unit to a train. So this means that the two people are on track for 4 minutes, 2 minutes to mount, 2 minutes to dismount. So therefore, Ryler surveys reduces the boots on ballast by 97%. So from the 352,000 number that I showed earlier, we reduce that by 339,500 on track exposure hours. And currently, a design tamping shift always requires the separate survey shift. And this survey shift can be eliminated with the use of Smart Tamp. So if we assume that a tamping night, the tamper machine is effectively 4 hours at the project location, the first hour is needed to do a survey run, set back, calculate and approve the compensation lifts and slews which to be applied. So this reduces the amount of time available for tamping by 25%. By having the full amount of time to complete a tamping shift minus the travel to site, the tamper will be able to complete 25% more per night. The opportunity to improve the efficiency of tamping machines, therefore, arises at locations where compensation tamping is currently applied. The information provided by Ryler surveys can be directly input into a tamper, and these machines will not have to execute a measurement run anymore. Only a short calibration run is needed. The only condition is that the design or alignment along with the Ryler data must be readily available. So for Network Rail, they execute compensation tamping on average every 5 years. So this means a scope of work of about 3,500 kilometres per year for compensation tamping. The costs for a tamping shift are approximately £8,000. So if a tamper can tamp 975 metres per shift, the price per metre is £8.21. But if a tamper could do that 25% extra and do 1,300 metres instead, the price per metre drops to £6.15. That's a saving of £2.06 per metre. So this would save around £66 million if all of the UK were to adopt the Ryler Smart Tamp. And again, on materials and maintenance, so this is the normal maintenance strategy for a 30-year life cycle of a normal plain line concrete track category 1. We can see on there's tamping, and currently it's set for 10 tamping shifts over the 30 years. But if we were to apply Smart Tamp, the potential is to increase the lifetime of all of the assets. So you'll notice that the current regime has lifted from 30 years to 36 years with Smart Tamp. And that's because there's less wear and tear. And the other thing to note on here as well is there's less activity happening across this site. So we've actually taken the tamping shifts down from 10 over 30 years to 9 over 36 years. And we can also look at the carbon as well that comes out. So for Network Rail, they produce 2.9 million tons of CO2. If we're to apply the 5% reduction, then we will save 144,600 tons of CO2. So that's over 175 million plastic bottles, or the equivalent of 66,000 tons of coal. And I also just went a bit further on the figures, and I just sort of checked through all of what Network Rail have spent over the last year, and just came up with other figures. These are actual figures they can be saving now: 301 million on their maintenance, 22 million within traction electricity. Again, the 339,000 boots on ballast and the 144,000 tons of CO2. And then, because obviously today I'm talking to you in New Zealand and in Australia, I also mapped that out again for Kiwi Rail. So the 30% annual maintenance saving would be 108 million New Zealand dollars. I couldn't calculate the traction electricity savings, unfortunately. I just didn't have time to find the figures. But for boots on ballast, we could save 35,500 boots on ballast hours and 4,000 tons of CO2. And for Australia, again, 30% annual maintenance saving, it's about 630 million Australian dollars and 333,000 boots on ballast hours saved. So we can overview everything that we've looked at, and you can see here, this is to compare the maintenance tamping, design tamping and smart tamp. So all three are safe and compliant, but with design tamping and smart tamp, you have the increased lifetime of assets, the 5% reduction of fuel and the 30% cost reduction, the increased tamper utilization. But Smart Tamp takes you further. So Smart Tamp offers the boots, 97% boots off ballast, the reduced survey CO2, your ballast management. Design data isn't just available for the surveys we've carried out for Smart Tamp. You can use that design data over many different projects. And it also gives regular infrastructure monitoring. And I think, just to take you back to the start, so on the quote that Nick had said about how plain line surveyors working during the day on undertaking track geometry surveys are at risk, well, he went a little bit further on that. And he said that converting this manual surveying to train-borne data capture was one of the primary reasons that near-miss frequency within the infrastructure projects track business significantly reduced. Ryla makes working in a rail environment that much safer. So I think I'd just like to finish by saying that design tamping is available now. I think it's just up to us now to go out and do it. So thank you very much.
Okay, thanks, Adam. Thanks for the presentation. We're gonna go over to the Q&A session now. We have a few questions coming in, dropping in. It's a little bit of various topic here. I'm just gonna take the first one from the top here. The first question is about the mounting of the Ryla system. So there's a question about the support of different coupling system on the locomotive around the world. Are there adapters for different locomotives? You're on mute, Adam.
Yes, thank you. Yes, there are. We have several different adapters. So that's part of our case, that we don't just have one adapter that fits. I believe that's a Schaffenberg adapter there, so we can fit to many. So recently I attached to a BSI coupler. We can also attach to Delna. We have, I believe it's about 8 different types of adapters that fit to most of the trains. And the other great thing is we can attach to almost any buffered train as well. So we have a buffer adapter. So if we can't attach to a coupler, we can always attach to buffers as well. So we do use locomotives, engineering trains. In the UK, we can attach to, say, we can attach to the 800 series, even though we haven't, but we can attach to the 100 series all the way through to the 700 series of trains. So yeah, we can attach to multiple. multiple different assets.
Okay, thanks for that. The next question is really interesting because a little bit of my background in terms of railway track, understand the track geometry. So the question raising the research that you are undertaking to investigate the compatibility of track geometry measurement system currently used in New Zealand or otherwise in other countries as well. With tamping methods currently used in New Zealand, the figure will provide parameters such as ROCODC, that is the rate of cant deficiencies, or dynamic rail corrugation measurement. So there are two things there, right?
Yeah.
One is geometry, the other one is rail corrugation.
So rail corrugation is being investigated, but at the moment we don't deliver those measurements. That's one of the few track measurements that we don't offer.
Yeah. So going back to the geometry, undertake and investigate the compatibility of track geometry. So maybe going back a little bit of comparing the system to the track measuring trains. Huh?
I think that's probably more of a question for David actually on the New Zealand side. That's not something I've investigated. So obviously I'm UK based, so we work very much within the UK and Europe to compare our system to track geometry measurement systems that are currently used across Europe. As you saw on the screenshots there, we're always trying to compare ourselves to a TRV. We have compared ourselves to a new measurement train in the UK as well, and yeah, I'm quite pleased of how Ryla stacks up to them. But for New Zealand, maybe that's a question David can answer.
Yeah, thanks, Adam. We have not yet, but we're working with people such as the team from Raileyes to do some of these comparisons and are looking forward to partners. However, we have been working with other elements of people within Australia in terms of the track geometry measurement systems they're already using, and it's very close. And yeah.
Okay. Thanks. Just to continue a little bit on geometry questions. So I just want to bring back to what you discussed before, the increased tamper utilization. Traditional. You had a picture comparing the traditional method where you go out, you measure it, and make the decision to tamp it, right, versus to having the rider on board. So what you're saying in the InnoTamp projects that the process is having somebody out on site to understand the geometry as well as making the decision to tamp that geometry in place?
I think actually, so with Ryla and with Smart Tamp, one of the things we can also do with Ryla is monitor the infrastructure. And in a very, very simple way, we can just, let's say we're looking at a main route that we know that will need tamping a lot. If we're monitoring that main route over a period of every 4 months with just one single run, we can quickly understand where the track center line is. And once we understand if that track center line's moving, we can make the decision to investigate the data more and make the decision to tamp from the data that we provide. So I think that's probably quite an important point, that even with our monitoring activities and decision making, we're still keeping people off the ballast, really.
Okay. Let's continue on the geometry and going into more accuracy of the topic here. So a question about what accuracy is required from the GPS and IMUs. How do they go when the GPS is obstructed, such as through tunnels, forest?
So for obstructions, so we do regularly carry out surveys where we go through tunnels. If a tunnel is, so we start getting the drift about 150 meters into a tunnel. So we're all right if a tunnel's 300 meters, quite honestly. But what we can do is we can add control points into a tunnel. So we can start referencing to a local grid within the tunnel. or we can even just use, if say we were to do my old neck of the woods, London Underground, we can actually connect to real points of infrastructure as long as they have the data of where that is. In terms of, sorry, the start of the question was, sorry, what accuracy is required? So in terms of accuracy, that was on one of my slides. So we have we got a 12 mil and 8 mil accuracy with GPS and IMU, and the rail and the laser head scanner, of course, which gives us the track center line.
Okay. So it's worthwhile to explain the. I recognize that you use the terms of relative track geometry and absolute track geometry. Can you just clarify? So I think many people
so
are asking about that.
Absolute is where we are. Where so let's, where I am from that sign is relative. Does that,
Okay.
Sorry. Did everything stay on there? Because I just managed to hit a plug and turn my screens off for a second.
Yeah. So we were missing out 3 seconds from you.
Oh, okay. So sorry. So yeah. So absolute position is, let's say it's where I am. That's your absolute position. That's what we measure. Yeah, in space. And then if you are to measure from me to that sign behind me, that is the relative position of that sign.
Okay. Thanks. Another question about.
I'm not a surveyor, by the way. So if someone does want to jump in and talk over my schoolboy logic, I'm more than happy for them to, by the way.
Yeah, probably at this point, just then also going through the tunnels and the accuracies and things. One of the unique elements of the RILA system is those track-borne LiDAR sensors that we are then able to use to calibrate track against itself across multiple acquisition times. They have a much higher accuracy level than the 360-degree LiDAR scanner as well.
Yep.
And so that's probably one of the unique propositions there. It's something that we have a patent for in Australia and across US and Europe. That also ties in really nicely in terms of that IMU drift and the dead reckoning question there that I see also coming up, Michael. If I'm just going to start to answer that, if that's all right.
Yep. Go ahead. Yeah.
So yes, it is essentially dead reckoning whilst in tunnels and when the GPS has dropped out. However, obviously you get both ends of the tunnel when it's a short enough tunnel, as Adam said, and tying into local control where possible. And we have done this with a number of underground tunnels and underground services for metros. It is also an area of interest to continue to work with partners and interested parties on how do we continue to improve our accuracy in tunnels and obstructed areas. So for some of you who I know are interested in those areas, please don't hesitate to reach out.
Okay, thanks, David. I have a question regarding about the track design. Going back onto that, right? Is it proposed that track design done by onboard software or existing track data used as an input for track designers? Now, this question is maybe more of a software question, but how does so
RILA, we do no processing on board of the RILA system, and that's that's one of the reasons why it's so light and we can move it around, makes it such a mobile system. We download the data and we transport that to our offices, and then we can carry out any design from there. But we're quite open, I think, on that question. Really, can we design the new track position if that is what the client wants? Some clients will want to design the track themselves. That's part of their safety case. That's part of what they do. So it's something, yes, we can provide a track design if that is what the client wants, or we can help get the raw data into a position for the client to design from that themselves, and then we can convert to an ALC file, let's say, and for that to go into the tamper machine and the tamper to carry out his tamp.
Okay. We have a question about the design tamping, and when we say design tamping, does this eliminate reduced design efforts for track designers while undertaking the regression-based work and eliminate smooth tamping, which sometimes done at site?
So yes, that's ultimately what we want to do, is eliminate the smooth tamping, because it's effective as a way of keeping a track operational, stopping things coming off the track when they shouldn't. But ultimately, it will lead to poor compound curves, etc. And so we will. That's what design tamping, in the UK especially, design tamping has always been a goal that we want to achieve. But the things that stop it are safety, money, etc. And now with Ryla Smart Tamp, it offers us the chance to actually design tamp everywhere instead of just selected places. In terms of design effort, I wouldn't say it reduces the design. It actually makes the design part a little bit, people now really need to design the track to an optimal position. That's what we're aiming for. Smooth tamping, you're just, you're letting the tamper do the work. So there will be more work for designers.
Okay.
That's good. That's good though, right?
So as a designer, I've been designing track for quite a while, and I would see the one thing to collect data with consistency is incredible important, how the result of the design will be. So that rule, right? Crap in, crap out. So that means that if we can have a consistent method to collect data, would be great for us as a designer.
Exactly, yeah. And I think the slide on for repeatability really showed the data we provide is consistent, which again, that's the most important thing, isn't it? I used to collect all of the cant, gauge, etc. manually, and we know that just swapping a gauge can sometimes throw you out by 3 millimeters. With Ryla, we don't quite have that same problem.
Yeah. I have a question about there's some question about here the services that Fugro is doing. So how does Fugro charge for the service? In general, do you have full service program available to manage the inspection and the processing of the design tamping data? Would that be an agreed metric or time period? How is it in UK, by the way?
So in the UK, it's we like to work in longer term contracts. So we'd like to work in a sort of, let's say, a 5-year partnership, because that's really the full extent of what you can get from the first baseline. So what we do is we have to obviously know the size of the scope. I can't offer any pricing without understanding what the size of a scope is. And it changes a lot. So again, I can't give a yardage price or anything, because we need to understand how many shifts would it take to collect the baseline, how many shifts will it take to do the single run. All of that needs to be worked in. But obviously what we try and do is work with the client, because everyone's got a budget to work to, and being the any salesman that just says, right, this is how much it costs, I want it all up front, they're not going to survive very long in this world, are they? So we will work with the client to try and split the cost over however long that contract is. So if it's 5 years, then we can work out the baseline cost, work out the single run costs, and we can just try and literally fit in a monthly fee to that. Is how I see it working most of the time within the UK. That's, for me, I think that's the best way. But okay. Yeah, obviously we're always prepared to work with clients to make that as easy as possible, really.
Yeah. We have someone that would like to ask about the frequency of the capture of the information here. How does the Ryla system work with track recording calls? Does it replace the need of track recording calls and reduce the frequency?
It depends what type of data you are collecting, quite honestly. So for track geometry, for gauging purposes, so in the UK we have some issues with gauging over here at the moment, but we can replace gauging trains and we can replace track geometry. But PLPR, you'll still need to run that. Ultrasonic testing, of course, we can't do that yet. I don't know. I'm trying to think of a way I can dump water onto a track and send a shock through it, but I can't from the RILA system. So yes, we will be we want to replace some recording vehicles, but we won't be able to replace them all. It really depends on the data sets that you're looking for.
Okay.
And probably the advantage of that is that it can be attached to a passenger bearing or another load bearing train. So it's another scheduled train as opposed to having to schedule a separate maintenance run for some of those data sets that you want to have out and utilize on and on.
Exactly.
Yeah.
And actually, we can also connect to the recording vehicles as well if we need to, if we want to collect data at the same time.
Okay. We have another question regarding about the accuracy. Again, which GPS corrections are applied to get absolute accuracy down to centimeter level?
Can I boot that one over to you, David?
Yeah. What I might suggest is, Alex, give me a hoy later, and we'll have a bit of a chat. But the broad answer on that one is across the last 10, 15 years that we've been doing this with the team in Europe and whatnot, there's a range of corrections, both from utilizing the meterage and collecting the data multiple times to create an average of that based on the high level sub-millimeter lasers that we have. So it's sort of utilizing the data to correct the GPS and then the GPS to back correct the data and vice versa, a couple of different ways. Much more than that I can't go into right now because it'll just take us way over time. But that's really the short version, is sort of multiple captures. Obviously, the more times you capture, the better that you'll be able to get that average down. But also then the integration of the different laser sensors at that higher level accuracy.
Okay. Yeah, I mean, it sounds like it requires a little bit more time to broad out, I guess, the system work in with different type of units. I understand you have different type of lasers in the unit itself, right? And by that you can interpret from very high tolerance to lower tolerance where it's needed.
Yeah, that's correct. So the track profiling lasers have a very, very high scope of error accuracy.
Yeah.
Based on that internal laser and also the distance that they're shooting effectively. Whereas the 360 laser, you know, the broader point cloud laser that's designed to collect all the other asset information infrastructure, slightly lower, but it's good enough for what's required. If people are requiring higher levels of accuracy on other things, and we can look at how do we design that best and use the best, you know, package to deliver that. But effectively what we're trying to do is get the highest level accuracy on the track for the track geometry and that information there. And then the utilizing, you know, slightly more fit for purpose levels of accuracy for things like track furniture, your OLE, etc., where you have a little bit more play, let's say.
Yeah. Thanks. There are questions continues coming in. That's really good. It's big interest, of course, in the accuracy. But here's a question: does RILA integrate the distance-based measures such as geometry with the time-based measures such as corrugation?
David, can I boot that one over to you again? Sorry, mate.
You can, but I actually don't know the answer to that one.
Yeah, nor do I.
So again, I might suggest that person reach out to yourself or myself. And I don't know if you put your email address up, but we're both available both on LinkedIn and through the Figure website if in doubt.
Okay.
Exactly.
Okay. Can RILA be used for switching crossing track sections? The person saw the slides only mentioned about plain track, and ultimately for tamping at switching crossing tracks, which is
Yes.
different from plain line tracks.
It is. It is. So in the UK, it takes us. We will do an S&C tamping over 2 separate shifts. But rider data, we can use that across S&C. I would like, but you know, we would be looking to sort of how we went out and carried out the survey would be slightly different to how we run a plain line. Because obviously, with a plain line, we could just run straight through. It's nice and easy. If we were looking at particular S&C units, we would want to make sure we were collecting the data from that whole unit, which would just mean there's a bit more planning involved. But yeah, we can very easily get S&C data from Ryla as well, and we can. In the UK, different routes and regions measure their S&C slightly different. Some will measure from the back of the point, some will measure from closures, etc. And we can adapt our measurements to however the client would like to see those measurements as well.
Yeah. Okay. A few minutes left of the session here. Here's one interesting question: does the result of RILA consider the error due to vibrations?
Oh, that's a question that I've been involved with recently, actually, because I was up doing a survey in another part of the UK where we were quite low on a train and it was bouncing around. And the answer to that is yes. Do I know how the processors and data engineers done it? They are wizards as far as I'm concerned. So no, I don't, but we do take into account the vibration.
Yeah, part of that, as one of the other attendees has stated here, is the IMU accounting for that, and part of that is the knowledge of the system and other elements that go into it.
Yeah, yeah. Does the system have a back-end application software to analyze trend, it according to input-output tamping data?
Yeah, so that now makes me wish I'd put another slide in actually to discuss the rail data portal that we have. So yeah, we have our own portal, and we're constantly working on that. We put a huge amount of effort into how we display our data to our clients. And yes is the answer, especially with, and I mentioned track center line monitoring earlier. For Smart Tamp, that's going to be a major part of projects going forwards, and that is how we're going to display track changes to our clients through the rail portal.
Okay, thanks. Okay, last one. There is a question about the frequency at rail. I think we did answer that earlier, but hey, I think there has been a lot of questions. I think the most important topic or item I recognize through the question here is regarding about the tolerance, accuracies. Bear in mind that you know the speed that you can go through the network and scan it quite quickly. So as a designer, as an engineer as well, I would love to hear a little bit more at some stage about how that accuracy can be narrowed down from a very broad accuracy down to ±5 or ±8. I can't remember the slide that you show, right?
Yeah, so 12 and 8 with uncorrelated runs, but correlated runs we can bring that accuracy down to 5 millimeters. You know, at what up to 165 miles an hour. So it's it impresses me every day I see the system in use, and you know, I'm an old track guy that normally isn't impressed by much. So yeah, so very proud of this system.
All right, I think that's pretty much conclude the Q&A session too. I think that it's been a good session. Thanks, Adam, for waking up early or late. I don't know what.
It's just gone 2:25 in the morning here in London. Okay. So yeah.
Okay, we call it early in railway terms.
Exactly. This is half a shift, isn't it? Basically. Yeah.
So yeah. All right. Thanks, Adam.